Welcome to the first spherical moment. What is the defect form of Hall's theorem? The Hall's theorem is a celebrated theorem in combinatorics and graph theory. We shall state its version of bipartite graph here. Let G be a bipartite graph with vertix sets x and y. Hall's theorem says that G has a matching covering all vertices of x if and only if the size of the neighborhood of S is at least the size of S for all subsets S of x. We shall refer to this as the Hall's condition. Here, the n of S denotes the neighborhood set of S, that is the set of vertices y in Y that are adjacent to some vertex x in S. Given any matching covering X, the necessary condition follows, since every vertex x in X is matched with an unique vertex y in Y. This trivial necessary condition turns out to be sufficient, which makes Hall's theorem remarkably beautiful. We shall not go through its proof, as there are other videos available on this. Instead, we illustrate the use of the Hall's condition through an example. Let G be the following bipartite graph. To determine if G contains a matching covering X, Hall's theorem says that it's equivalent to checking for any subset S of X, the size of the neighborhood of S is at least the size of S. If S is equal to the singleton set containing x1, then the neighborhood of S contains y1, y2, and y3. And the size of the neighborhood of S is at least the size of S. If S is equal to the singleton set containing x2, then the neighborhood of S contains y4 and y6. Again, the size of the neighborhood of S is at least the size of S. We repeat this process for all the 1 subsets, 2 subsets, until we exhaust all possible subsets of X. And if the Hall's condition is satisfied, then Hall's theorem guarantees a matching covering X. There is a generalization of Hall's theorem known as the defect form of Hall's theorem, which was proven by all and perfect independently. Suppose G is a bipartite graph with partite sets x and y, and D is some non-negative integer. Then G has a matching covering the size of x minus D vertices of X, if and only if the size of the neighborhood of S is at least the size of S minus D for all subsets S of X. Put in a simplistic sense, the defect form says that when the Hall's condition is compromised by a difference of D, then there is a corresponding trade-off in the size of a guaranteed matching which covers D less vertices of X. Note that if D is equal to 0, the defect form reduces to Hall's theorem. Can you prove this theorem? Hint: alter the bipartite graph in order to invoke Hall's theorem. Pause the video here if you would like to give it a try. Let's discuss the proof. Given any matching that covers the size of x minus d vertices of x, the necessary condition follows immediately, akin to Hall's theorem. Suppose we represent the matching with red edges. Observe that there are d unmatched vertices in X, and any subset S of X contains at most d unmatched vertices. Hence, the neighborhood of S contains at least the size of S minus d vertices. Next, to prove the converse, suppose the size of the neighborhood of S is at least the size of S minus D for any subset S of X. In a similar way as before, it may be checked that the condition holds for this example with D equals to 2. In particular, when S contains x1, x2, x3, and x5, the neighborhood of S contains y2 and y3, and we have equality. How can we ensure the existence of a matching covering the size of x minus d vertices of X? Interestingly, this can be achieved by some modifications to the graph. First, add d vertices to the set Y, and edges between these vertices with each vertex of X. Then the Hall's condition is satisfied in this new graph. By Hall's theorem, there exists a matching covering X. Furthermore, at most d vertices of X are matched using the added edges with the added vertices. Removing these added edges, the matching now covers at least the size of x minus d vertices of X. This concludes the proof. Another generalization of Hall's theorem is known as the polygamous form. Let G be a bipartite graph with partite sets x and y, and k be a positive integer. Then G has a k matching covering X, if and only if the size of the neighborhood of S is at least k times the size of S for all subsets S of X. Here, a k matching covering X means that every vertex in X is matched with k vertices in Y, and no two vertices in X are matched with the same vertex in Y. When k equals to 1, the polygamous form reduces to Hall's theorem. Hint: a proof strategy similar to that of the defect form works here. That is, alter the graph to invoke Hall's theorem in showing the existence of a matching, then show that this matching reduces to a k matching covering X in the original bipartite graph. Can you figure out a proof? I will leave a solution in the comment. Share your solutions in the comment below too. Please like and subscribe for the latest video. Leave in comments any problems or topics you are interested in. Alternatively, you may email me. Thank you for watching.